Hello and welcome to the webinar within the project ARCC. Today's topic is interfaces in electrocatalysis, hotspots for green energy conversion pathways. And my name is Sain Gutic. I'm professor at the University of Sarajevo, Faculty of Science. Today, there is probably a small number of people who are not familiar with the terms energy crisis, fossil fuel depletion, global warming, and so on. However, energy crisis is not a scientific or a thermodynamical but political problem, as you know from first law of thermodynamics, according to which the energy of the universe is constant. In other words, we have a lot more energy around us than we can actually spend. And a good illustration for this is if we compare, for example, the total energy used by the whole population of the planet in 2016, it is 577.92 exajoules. And if we compare that amount of energy with the amount of solar energy that reaches the Earth's surface every second, we can actually see that the total annual energy use can reach Earth's surface in less than 2 hours, only from sun. So from the thermodynamics point of view, it is not the amount of energy that is problematic, because we have a lot of it. It is actually the other physical quantity or thermodynamic quantity that is usually misrepresented as some measure for disorder or something like that. It's called entropy, and it actually measures what portion of energy, of internal energy of some system actually we can convert to work. So entropy is much more than a disorder, because it has unit joules over Kelvin, and we cannot measure disorder in those units, but we can measure how much energy dissipates as heat when some system is doing work. And because of these things, actually, from thermodynamic point of view, we are not in energy crisis, but we are in entropy crisis. And actually, the whole materials science connected with the materials that are used for energy conversion actually is fighting a war against entropy, because we are preparing materials that can reduce the entropy of the system, or actually that can increase the quality of energy that we can store and then spend as we need it. Now it is a question how electrochemistry can help in solving these problems. One part of electrochemistry that is actually combination of electrochemistry and heterogeneous catalysis is particularly focused on these problems, because all of energy conversion and energy storage also in electrochemical systems is actually based on some chemical reactions that occur at surfaces or in some at some phase boundaries. So electrocatalysis is a combination of electrochemistry and heterogeneous catalysis. Is actually covers actually a lot of different chemical reactions and uses, applications. For example, electrochemical sensors in analytical chemistry, then electrosynthesis. But the interesting thing for this topic is actually electrocatalysis considered with electrochemical production of renewable fuels and electrochemical utilization of renewable fuels. So basically electrocatalysis is considered with the rates of electrochemical processes and how we can increase those rates or selectively increase those rates. So the selectivity is one important thing when we consider some electrocatalysts, because we want to catalyze just one reaction, one particular reaction, and other reactions should stay should proceed at low rate. The other one is activity, of course, the other parameter of good electrocatalyst. In electrochemical terms, activity means that we need low over voltage or low polarization to achieve high current densities, because current density is the parameter that is connected with amount of substance converted, and thus with amount of energy stored or released. And of course the third parameter is stability, which is actually important for real systems, because when we make electrocatalyst we want that we want that catalyst actually lasts as much as possible, and that, especially when we are considering electrocatalysts based on platinum group metals. Here you can see hydrogen fuel cycle and synthetic fuel cycle. Both of these cycles actually connect electrochemical production of fuel and electrochemical utilization of fuel. So on the hydrogen cycle, production means electrolysis of water. Of course, there are other ways to produce hydrogen, but we are dealing with electrolysis of water because it is when you use power from the renewables, it is actually the green method, and hydrogen produced by electrolysis of water with energy from green sources is actually called green hydrogen. So production of hydrogen means electrolysis of water. Then we have storage and distribution of hydrogen to pumps or to the customers, and at the sites where we need energy we have electrochemical, we can say, combustion of hydrogen. Of course, hydrogen can also be can also react directly with oxygen, but electrochemical process actually proceeds at low temperatures in so-called fuel cells, and is also a catalytic process, so we can control the temperature and everything, and we can actually we can use a lot more energy as work when we are oxidizing hydrogen in fuel cells. The same we can say for carbon dioxide. So we can actually produce synthetic fuels by the reduction of carbon dioxide. Here on the cycle actually you can see chemical step for the production, but there are also electrocatalytic steps, of course. So we can, on the electrode, we can electrolyze solution of CO2, and we can obtain some synthetic fuels that we can actually burn again, or also electrochemically in fuel cells oxidize them to again to have CO2 and water, but we can close the cycle so there is no net CO2 production. Electrolytic hydrogen production means that we are decomposing water between two electrodes with the help of electric current, from which we obtain the energy needed for this process. So on one electrode we have formation of H2 molecules, and this reaction is called hydrogen evolution reaction. On the other electrode we have formation of O2 molecules, of oxygen molecules, and this reaction is called oxygen evolution reaction. And regardless of the type of electrolysis cell. These two reactions need catalytically active materials that can provide surface for these reactions to occur at very low voltages or very low or potentials. Three most mature types of fuel cell electrolyzers are PEM fuel cell, proton exchange membrane, liquid alkaline, and solid electrolysis and solid oxide electrolysis cell. And the difference is actually mainly in the electrolyte inside of the cell. So PEM actually has an acid electrolyte, proton exchange membrane, and because of that we need to use catalysts that are stable in acidic environment. On the other hand, alkaline electrolyzer uses aqueous potassium hydroxide, and we actually can use some other metals that are not usually stable in acid environment but are stable in alkaline, like nickel. On the other hand, materials that are used for the electrode where oxygen evolution reaction occurs are more or less the same regardless of the acidity of the electrolyte. On the mechanism of hydrogen evolution reaction, in the mechanism you can see the difference between acidic and alkaline electrolysis, where in alkaline electrolysis actually the reactant is water molecule H2O, which slightly can decrease the rate of a reaction. And actually the engineering of electrocatalysts on the nanoscale to have some surface, some phase boundaries between different materials is done because of the first step, which is not shown here, and it is actually the dissociation of water molecule. We don't have that problem in acidic electrolyte. In acidic electrolyte, actually we can platinum nickel has very good activity, but it is not stable. It corrodes very fast, so we have to use platinum, which is very expensive. On the other hand, in alkaline electrolytes, we can use nickel, which doesn't have activity as good as platinum, but it is stable enough and cheap enough, so we can use it in electrolyzers. So now when we have hydrogen produced from renewable sources, we now have to burn it to take the energy back. We can do that by direct combustion in internal combustion engines, or we can oxidize it electrocatalytically, which means in both cases we actually get water as a product. But in electrochemical process, actually in electrocatalytic process, where oxidation of hydrogen occurs at the electrode with simultaneous reduction of oxygen on the other electrode, we have possibility to extract much more work from the energy contained in the mixture of hydrogen and oxygen. So this reaction is actually just the opposite of the reaction that we discussed previously. So we have a combination of hydrogen and oxygen into water molecule. Reaction mechanisms for each of electrode reactions are complicated, but here you can see that actually we have the same technologies based on different electrolytes. We can use hydrogen fuel in alkaline fuel cell, in proton exchange membrane fuel cell. Here you can see our research activities in brief, and you can see how they fit in these systems and these problems. We are mainly considered with electrochemistry of graphene-based materials, which means that we uh, uh, do research of pure graphene materials, graphene-based of electrochemistry, of course, of pure graphene-based materials, and the possibility of tuning of these materials to achieve some desirable electrochemical properties. But we are also considered with graphene with the composites of metallic and metal oxide nanoparticles with different graphene-based materials. So we are preparing and testing these materials for hydrogen evolution reaction and oxygen reduction reaction. One is the reaction that is used in for the production of fuel, and the other is used for the utilization of fuel in fuel cells. So we do this with different experimental techniques, but also with theoretical techniques, with theoretical methods like density functional theory and kinetic Monte Carlo. And we test these materials on small scale, but also on medium scale. One interesting approach that we use is to drop cast graphene oxide on the metallic substrate. Usually this metallic substrate that is not active for the reaction that we want to use, and then evaporate the solvent, and then simultaneously reduce the graphene oxide film and deposit the metallic particles. So you can see this here schematically, and you can also see some electrochemical results, some Raman parallels, and also some Raman spectroscopy results, some Raman spectra of these surfaces. So in this way we can actually control the amount of metal on the reduced graphene oxide, and of course then we use the scanning electron microscopy or transmission electron microscopy to see what we have. Here are some results obtained by DFT calculations. As you can see, if there is no vacancy on graphene surface, if there is no defect, then the nickel molecules actually interact with each other and form a cluster, then nanoparticle or crystal. But if there is a vacancy on graphene, the vacancy is the part of graphene structure where there should be one or two C atoms, but they are absent, and so this is the place where they with high energy, which can actually stabilize atomic nickels or nickel clusters. So to achieve the good dispersion of nickel nanoparticles on graphene surface, it is important to have a graphene with a lot of structural defects. Also, we calculated the graphenes with different oxygen groups. On the next slide, you see some electrochemical results that actually show how the hydrogen evolution activity evolves with the quantity of nickel deposited on reduced graphene oxide. So firstly, electrocatalytic activity increases, then it reaches maximum, and if you continue to increase the quantity of nickel, it goes back to the activity of pure nickel, which means that actually we have the best electrocatalytic activity or the best electrocatalyst when we have some optimal ratio of nickel and carbon atoms, or when we have interface between graphene and nickel nanoparticles, which is schematically shown here. So the interface between these particles is actually responsible for water splitting, but also for hydrogen spillover. Both of these processes actually could increase the overall reaction rate, and this is not true only for nickel, because we did a lot of experiments with other metals and also alloys like nickel molybdenum and iron and cobalt and also platinum, and all of these metals actually show the similar behavior, except for platinum, of course. But iron group metals show similar behavior. We have increased and increased catalytic activity. So this is why we think that interface between graphene and metal is actually very important for achieving the highest possible activities when you have pure metal on graphene surface. So to summarize, we recognize the importance of graphene-based materials as supports for electrocatalytically active particles, and we are actually also doing research about different electrochemical behavior and possibilities for modification of these materials to achieve best possible catalysts. Our research is currently supported by two projects. One is the NATO Science for Peace and Security in collaboration with National Institute of Chemistry in Ljubljana, Slovenia, and the University of Belgrade Faculty of Physical Chemistry in Serbia. And the other is a project funded by Federal Ministry of Education and Science of Bosnia and Herzegovina. You can see some of the outputs of our NATO Science for Peace project. We have scientific outputs, of course, scientific papers that we publish, but we also have technical outputs like our catalysts, platinum-based catalysts, and the prototype of the fuel cell, PEM fuel cell, that contains our catalysts. So in this project, students are actively involved. They are doing the research. They are also doing the technical parts, development of the prototype, testing, and other things. The knowledge and the experience that students gain working on this project is very valuable and is very important for the green energy transition, because they deal with problems at the most fundamental level of the energy conversion and storage, which is of utmost importance for systems that will be used and that are already used in green energy technologies.